Now we will have BBH simulations with CapyrX and CanudaX by Lucas, Timotheo Sanches. I think I mispronounced your surname and your middle name incorrectly, but yeah.
Don't worry about
And he
it.
is a postdoctoral researcher at LSU. And like similar to Livei, he is actively contributing in many parts of the Einstein Toolkit. And we will be hearing from him now. Yeah, you can
All right.
continue from this. Yeah.
Okay, thank you. Firstly, I'd like to thank everybody for organizing the meeting. This has been a great experience so far. Everything is running very smoothly. So thanks for having me here, and thanks for being here for the last talk of the day to listen to me ramble a little bit about multi-patch systems in CarpetX, right? So, like Behan said, my name is Lucas. I am a postdoc at LSU at the Center for Computation and Technology, right? Working directly with the Einstein Toolkit group and with Stephen Brandt. He is my direct person responsible for me in CCT at LSU. And today I'm going to showcase to you the current status of CapyrX, and I'm going to try to showcase some results that we have been able to obtain so far, and kind of give you a guide, an idea how you would adapt your science codes to use these multi-path systems, right? So here we have our little logo. As everyone knows, a logo is the most important part of any scientific code, right? And this logo represents, this was an effort started out a few years ago between me and Eric while I was still a PhD student, right? And so here we have the capybara and the beaver. That's where the name comes from, right? The capybara is the largest rodent in Brazil, and the beaver is the largest rodent in Canada, and they're weaving some coordinate tapestry together, right? I really like this logo. Uh, so moving on, talk a little bit about the team, right? So we have three main developers so far. That's me over here on the left, and then, well, you all know Eric, right? And you all know Stephen Brent. They are very well known across the Einstein Toolkit community. I am hoping to expand that. Maybe we can use this thing as a little bit of a recruitment drive to get more people interested in contributing to CapyrX and porting their science codes to CapyrX. Right, and so let's begin by talking about what is a multi-patch system, and then we'll talk about why we want to use them, right? So basically, the idea of a multi-patch system is that you're going to cover your simulation domain with multiple different coordinate systems. And there's a few reasons why we want to do that, right? But this is something that's mathematically very natural to do in general relativity because, as you may be aware, coordinate charts and coordinate maps, they are gauge freedoms. We can play around with coordinates as much as we want, right? So we have the space-time manifold of interest of the problem we want to solve, and we usually simulate in our computers like a subdomain, submanifold of that big manifold, right? We can cover the submanifold with different coordinate systems. So here in this chart, what we are trying to show is that you can have some sort of global Cartesian coordinate system, right? That's covering this submanifold here. But within this global Cartesian coordinate system, you can define some different coordinate patches and different coordinate charts that, of course, they cover the global domain, but they also do that in a way that when you embed them in this global Cartesian system, they're going to have some sort of symmetrical symmetry effect, right? So you can have spherical-like coordinate systems and such by doing that. And that is very, like I said, very natural in numerical relativity. Now, of course, having a global coordinate system that encompasses your multiple coordinate patches, this is a choice. It makes things a little bit easier on the application writer side. Of course, I don't want to get really into technical details about the difference of those, but in principle, you don't need to have that to have a functioning multi-patch system. You could, for instance, delegate the fact that you're using different coordinate patches to complicated boundary conditions, right? So like you put all the complications in the boundaries, and then you deal with the fact that your complications are in the boundaries. But doing things this way means that basically what we're going to have to do in the future is that we're going to have to adapt our codes to these coordinate patches, is that we're going to have to change our derivative operators. Because when we do derivative approximations, usually doing finite differences, right? This is something that's very popular in the Einstein Toolkit community. We use, these are all implicitly referring to the local patches, right? So you're taking finite differences with respect to these local coordinates. Um, but then you want to combine expressions and you want to do your math in the global coordinate system. So there's going to be some projections from local to global coordinate spaces with the derivatives. I want to showcase that on code later on, right? But so to summarize, right, the idea is you are covering your simulation domain with multiple different little pieces, multiple patches. They all fit together, right? And there is some known transformation between the local coordinate patches and the global coordinate system, and from the global coordinate system back to these local patches, and the derivatives of these coordinate transformations, right? With that information, you can adapt your code, and you can have a code that works with these um, multiple coordinate patches. Now, that's introducing a lot of complication and something that could be straightforward. For instance, why not just get like a big old Cartesian grid and just do my evolution in a big Cartesian grid, right? Why do I care about that? Well, there are basically two reasons why we care about that. And reason number one is what I'm calling here grid efficiency. So let's do some sort of back at the envelope mental exercise calculation. Suppose that we have some Cartesian grid with some grid spacing delta x, with some extents delta x and delta y, and some grid spacings hx and hy. Now, let's suppose that for some reason we want to make this resolution here finer, right? We want to add a resolution, either because our physics requires that we add more resolution, or because we're doing a convergence test, or because anything of the sort, right? So how many extra points will we need to store if we do that, right? So if this is the quantity that the amount of points we will store for this base grid, right? This is the amount of points that we will store for the refined grid with respect to the N1 original grid, right? So suppose that you make this delta factor here by which you going to refine your resolution, right? Let's suppose that you make them equal in the x direction and the y direction. This is telling us that this thing is going to scale with the square of the refinement factor you're adding here, right? So this translates into a lot of extra points you're going to have to store. Conversely, we might want to make our grid bigger, right? So suppose that we have, again, some original Cartesian grid with dimension delta and spacing h, and we're going to increase it because either our physics requires that we make our grids larger, or because we are trying to do something else, right? So if we increase our grid by a certain factor delta here, right? How does that scale, right? How many extra points will we need to store? And again, if you look at the math, you're going to see that you have a delta square proportionality factor here, right? So it scales with the square of the amount of extra spacing you want to add in your Cartesian grid. So this is not very efficient, right? It's if you do that in 3D, of course, then this is going to be a cubical scaling, and then things are just going to be even worse. So again, consider that you have some cubical grid with constant dimensions delta and constant grid spacing h, right? And assume that you want to store 8 bytes per floating point, right? And suppose that you want to change the domain size of this cube here while keeping the grid spacing fixed on point 1. Right, so if you go from 100 to 400, you're going to see that your storage requirements are going to go from 8 gigabytes to 512 gigabytes of memory. And that's for like a single grid function or a single variable that you're trying to evolve, right? And something similar happens here if you change the grid spacing, right? Sorry, I think I got these the other way around. So if you have a fixed grid spacing and you increase the resolution, you see also uh, an exponential growing effect in the memory requirements, right? And that is bad not only because we're using more memory, but because the more memory we use, the more loads and stores, the bigger our grids are, the more inefficient our computations are going to be. And the reason number two why we care about this is boundary trash, right? So our simulations, they do not extend to infinity, and eventually you have to say, okay, this is the end of my simulation domain, and I have to do something about this artificial numerical boundary that I am creating that simulates the far away. Now, of course, there are different techniques to handle that. There are different kinds of boundary conditions you can impose, right? But usually they are like transmitting, absorbing, or dissipating boundary conditions. But none of them are perfect, and they cannot be perfect. And there's always going to be some sort of numerical spurious reflections that come back from that boundary. Now, if what you're trying to do, for instance, is to simulate gravitational waves, you want to pretend that you are a detector that is very far away from where the center of action, the merging black holes are, right? So if you want to place your detector very far away in the simulation domain, you need to make your grids bigger, and you need to make them big enough in such a way that the outer boundary radius that you're selecting for your grid, whenever the trash radiation comes back from that, it will not overlap and interfere with whatever data you're measuring, right? So basically, we want to have high resolution and we want to have large grids, right? So you want our cakes, we want to have our cakes and eat them too, as they say. So what we have to do here is we have to try and use some grids that have a better efficiency in the sense that they are better suited for the problems we're trying to solve. They are more adapted to the physical symmetries of the problems, right? So in particular, let's suppose and then we don't do our simulations with a Cartesian grid. Let's suppose if we're going to use like a spherically symmetric grid, right? They are more efficient because you can scale the radio and the angular resolution are decoupled in these grids, which they're not in Cartesian grids, right? So you can have a grid have a lot of radio resolution, and then you're just increasing linearly the amount of points that you need to store, and not no longer exponentially, right, as you would on a Cartesian grid. Of course, the problem of doing that is, as we know, spherical polar coordinates, they have coordinate singularities. So we already have enough singularities as it is in relativity. Do not want to introduce new coordinate systems that gives us new singularities. So what do we do about that? Well, this is where the multiple patches come to the rescue, right? The idea here is that you're going to cover your simulation domain. You're going to use spherical coordinates, but you're not going to use a single coordinate chart in order to describe the surface of your sphere. You're going to use multiple coordinate charts. And you do that because when you combine these coordinate charts, you can cover the surface of the sphere without introducing any coordinate singularities, right? So here we're seeing two examples of such coordinate system. The coordinate system here on the left, I like to call it Thornburg 6. As far as I know, in numerical relativity, Jonathan Thornburg has introduced these coordinates for apparent horizon finding and for multipatch systems as well, right? So the idea is imagine that you have a cube, right? And now imagine that your cube is malleable, it's rubbery somehow. And then you are going to with some device, you're going to inflate that cube, right? Until it turns into a sphere. Now, what's going to happen is that the six faces of your cube are going to turn into spherical-like caps, right? And they're going to be put together in a perfect sphere. And this is going to be covering, so if you turn each of these faces into a coordinate system on itself and you join them, you're covering the surface of the sphere and you have no coordinate singularities at the poles or anything like that, right? So this is basically what we're seeing here. And this coordinate system is very popular in numerical relativity, has been used in many applications so far, right? There is only a little caveat here, right? Because the way that this thing is constructed, the center of our coordinate system here is you're going to, have a spherical like inner boundary to your coordinate system, and that is fine if what you're doing is, for instance, if you're doing like a single black hole, you can put the inner boundary inside your event horizons, right? And then everything should be fine. If you're doing binary black holes, this is going to be a little bit more difficult, right? Because usually the things that's happening is happening right here in the center, and you need to capture that somehow. Or, for instance, if you have like a neutron star merger, in which, the fluids are doing all sorts of crazy stuff and you don't have any kind of symmetry. You really want to have some sort of grid that captures that non-symmetry in the center. And so this is why grids like this have been used before in numerical relativity, right? So what you have here is you have a central Cartesian patch, and then you surround that Cartesian patch with 6 spherical-like quasi-spherical caps. They are not exactly spherical. If you look at the math here in the coordinate definitions, you're going to see that these are not exactly spherical in the same sense that these things are. But what you can do, of course, is then after you do this, then you add another layer here of patches to make them become exactly spherical at the outer boundaries. And what these patches are going to do is that they're going to interpolate smoothly from a flat surface of a cube to a curved surface of a quasi-sphere, right? And this is going to be very efficient because grid efficient, because then you're going to have your spherical outer boundaries, right? Your quasi-spherical outer boundaries, and they're going to be very spherical if you place them far away. But you're also going to be able to capture whatever action you want to capture here in the center. And you can do adaptive mesh refinement in this Cartesian grid and so on and so forth, right? So this is this is how we do things. Now, of course, when you do that, I think I went back, right? Of course, when you do that, you introduce a new complication, right? If you come back here, you're going to see that you have new artificial boundaries in your domain, which are the boundaries created by whenever 2 patches touch. Now, there is a few choices of things that we can do here. Basically, 3 things we can do, right? So imagine that this green bar here is your patch touch zone. This is your intra-patch boundary. And these filled points are interior points, and the non-filled points are ghost points, which need to be filled somehow in order to have well-defined stencils. So the first thing you can do is you can have the patches simply touching. Now, of course, the problem if you think about this as like a stencil computation, right? What you're doing here is you're going to have to make your stencils further and further one-sided when you get to the boundaries. And then at this very boundary point, the last point at the touching points, they're going to have different values, right? Because with this patch, this square here is going to be filled with all the information to the right of it, which is potentially different from the information to the left of this guy here, right? So you're going to have an interface where discontinuity is going to arise. And the way that you treat that discontinuity is by doing what I am calling here characteristic exchange. Now, this is relatively uncommon in numerical relativity. You need a first order evolution code, and you need to know what the characteristic variables of your evolution system are, and that is not easy to compute. That is not trivial to do, especially for something like the BSSN system. But if you have that information, what you can do is you can do summation by part derivative stencils with what's called the simultaneous approximation term, or SAT boundary conditions, where this discontinuity is going to be smoothed out by the exchange of characteristics from the left and right patches. Now, a simpler approach, which does not require you to reformulate your code, is approach number 2 and 3. Let's start with approach number 3. This is the approach that Llama, the current carpet multi-patch system, takes, right? So you have overlapping patches plus ghost zones. So you make your patches not only you don't make them touch, but you make them slightly larger than the interpatch boundary so that they have some overlap. And you add some ghost zones to that. And you add all of that information, right? You use these overlaps to fill the ghost zones in the opposing patch, right? This is how the data flow looks. And finally, the approach number 2 is you still have your touching patches, but you still add some ghost zones, right? So that you can still use, for instance, the centered stencil here. And now, of course, the problem is you need to fill this with information from the other patch. And this is exactly what you do, right? You use one-sided interpolation onto the ghosts. And so currently, we CapyrX is supporting number 2 and number 3. We have overlapping patches and ghosts, and we also have touching patches plus ghosts. In principle, there's nothing stopping us from doing number 1. It's just a matter of having a evolution system that actually allows us to do the SAT boundary conditions, which is not trivial, and this is a lot of work. So it needs you to write a new kind of PSSN formulation and so on and so forth, right? So what's the status in CapyrX? Well, CapyrX, I believe, is ready to be integrated with your physics applications. So the infrastructure is there. We have been testing it for a while now, and I am fairly confident at this point that the basic infrastructure for doing the multi-patch derivatives and patch communications is indeed working, and I'm going to showcase some examples of it working. Currently, our efforts are focused on integrating it with CanudaX. CanudaX is a carpet export of the Canuda code. The Canuda code was developed by Helvi VTech. She's and collaborator. She's going to give a talk tomorrow, right? And I think probably the people in the European numerical relativity community are very familiar with that, right? So CanudaX is the carpet X version of that, and I have decided to modify CanudaX to support doing binary black hole evolutions and others with multi-patch system. And of course, most of the effort is now focused on that, and there's a lot of kinks to iron out, right? There's 1,000 little small things that need to be fixed and need to be changed in order for this to work. So for instance, one thing that we do not have yet currently is apparent horizon finding, right? So we do not have that capability yet. I have not adapted our horizon finders to work in the multi-patch context, but we have puncture tracking, sort of. The puncture tracker is tracking the punctures, but there is some bug in the code I'm still not very clear on what's happening there, but still needs investigation. Some other things also need to be done, right? So basically, we're investigating what happens, for instance, when the vial scalar interacts with these patch corners, and some interesting reflections can happen there. And then you have some sort of like horn-like structures that propagate through the corners. That's pretty interesting. So, we're trying to understand these things here and there and trying to iron out all these kinks so that we can have a functional application in that. But like I said, I think infrastructure-wise, the code is ready to be used. And if you're a scientist and you're interested in numerical relativity and you want to do something, now it's a good time to start working on this, because I think the major bugs have probably ironed out. So you can still do something cool, but hopefully not that difficult, right? So So here I'm just going to leave my references for the images that I've used. And now I would like to showcase some of the code side. Now this is going to become a little bit more like a coding talk, and I want to show you guys how things change in code and some results of CapyrX. So I think I have 45 minutes and I'm still doing good. But if you have any questions about this part, I think we can take them now. If not, we can just move on.
I don't see any questions in the chat. Jay Kalinani.
Oh, Jay has his ring.
Jay, please
Yeah.
unmute yourself. Yeah.
Hi, Lucas. Thank you. Are you able to hear me?
Yes, we can hear you.
Oh, yeah. Thank you. I just wanted to ask about the interpatch boundaries. So are these boundaries you share a common vertex, or is it the common, like a face that you share between at the interpatch boundaries? And in terms of support, how does it work when you have like edge-centered or face-centered variables, and what exactly is done for those variables at these interpatch boundaries?
Okay, so to answer your first question, we construct the patches to be touching, and we construct them to be like this picture here. So that means that in the patch interfaces, the Cartesian and spherical-like patches share a face. So that's good. That's what we want for Hydro, and that makes things easy for Hydro. Now, your second question is, if you have a face-centered kind of variable, right? Like a variable that lives right here in the edge, in the center of this face. How you would treat that? I think this is mostly a, this is probably something that you as the scientific application developer could choose, because I think you can create your face center variable with ghost zones, and then this kind of thing applies, right? So like your variable lives on the face, but there is a ghost zone, and the ghost zone of that is extending in the other patch, and then you're gonna do these interpolations to do things. I'm probably talking nonsense because Eric has his hands raised.
Yeah, Eric, please go ahead. Yeah.
Yes, go ahead, Eric.
So the faces and also the edges and vertices exactly aligned on the interpatch interfaces. Currently, the function is double valued. That is, both patches have independent values for the vertices on this touching face. And clearly for Hydro, you then have two different fluxes there. You would have to unify them to make Hydro work there. It's a local change, so fairly straightforward. And then you have matching fluxes on the interface, and then you should get exact conservation in a Hydro code. So it's very close.
Yes. Yes, that Eric said what I wanted to say in a more coherent way, which is that like you have this information like this diagram, this information is duplicated across the patches, but it's basically you can choose what you're gonna do with that, and you're gonna have to somehow manage to make that reconcile that potential differences, and the way that you do that is depending on your scientific application, I would say.
Lucas, we have two more questions in the chat.
Okay.
One, Amen asks, does the interpatch boundaries for multiple patches work smoothly for any dimensional manifolds?
Does the n-dimensional interpatch boundaries work for n-dimensional manifolds? I'm not sure I understand the question. But I'm going to answer the question, which I think you're asking.
Yeah.
So the multi-patch boundaries, they are an artifact of the coordinate charts where you're choosing to describe your R manifold, right? So you have a manifold, you have to choose some coordinate system to describe it. We just happen to choose multiple coordinate charts or coordinate maps to describe them, and we construct these coordinate maps in such a way that they touch and they coincide at these boundary points. You could construct them in an arbitrary way, of course, but for our practical purposes, this is what we want to do.
Yeah.
Does that answer your question?
Amen. Is that answers your question? Yeah, he says thanks. Thank you,
Okay.
Lucas. There is another question by Kate. He asks, can you compare and contrast your work and NERPy?
Compare and contrast my work against what? Sorry?
NERPy,
okay, against NERPy. Well, okay. Sure. In principle, you would be able to implement the same kind of coordinate systems that NERPy implements with CapyrX. One of our design goals is to be able to allow you to extend these coordinate systems to crazier and more interesting coordinate system than just, this, right? There's nothing wrong with this coordinate system. It's perfectly fine. But if you want to do things like, for instance, NERPy is doing with their coordinate system, things that are more advanced, you can extend CapyrX to that. And we tried to design the code in such a way that it would be easy for you to do that. I hope that I have succeeded in that design goal. I mean, I'll need users trying to use it to tell me if that failed or not on that endeavor. But yeah, I think this is the basic comparison. I'm not trying to do things. I'm not that you could implement the NERPy coordinate systems in this, but so far we do not have the same support of coordinate systems that NERPy is using. All that we support basically so far are Cartesian grids and grids like that, but this can be extended in the future if you want to.
Thank you very much, Lucas, for your answers. That concludes the questions in the chat for now.
Okay.
Yeah.
All right. So for the remainder of this talk, I want to give you some preview of some results. That means showing you some movies, which is, of course, why we do this, right? We're just seeing cool movies of things evolving in grids. So first, we're going to start with some slightly boring, but still useful wave toy examples, right? And so what we're looking at here is our y slice, y equals 0 slice of a spherical Gaussian post. It's going to start at the center and it's going to evolve outwards. Here, I want to showcase that we have absorbing boundary conditions ready, right? So whenever our Gaussian pulse reaches the boundary, it's going to be absorbed by the outer boundaries. I'm just going to hit play, and then we're going to see. So I'm hitting pause, right? So this is our spherical Gaussian pose. It's an important thing to note here is that it propagates as it should across the patches. The patch interfaces don't introduce any sort of artifact of it. Oh, also important to mention, this pulse here is scaled by the radius, right? So you're not only seeing, because when you have a Gaussian pulse and it propagates out, the amplitude decreases with the radius. So if you multiply the amplitude by the radius, you should get a pulse that's basically, mostly of a constant height. And that allows you to see if your multipatch system is introducing undue artifacts and things like that. Of course, there will be reflections whenever you go across interfaces. That is inevitable. But I'm just going to continue the movie so you can see. You have your Gaussian pulse here absorbed by the grid. I'm not sure if this is visible on Zoom, but you can still see that your absorbing boundary conditions still produce a little bit of reflection, which again focuses on the center. I probably can see that over Zoom. It's going to be hard, but it produces a smaller reflection, and you can see that by looking at the scale of the min and the maximum values here of our Gaussian pulse, right? It focuses again in the center, and then it propagates out again back to the boundary, and it keeps doing this ping pong game. And whenever it goes across the outer boundary, the values get smaller and smaller. And if you look at that, you can see that the values are going smaller and smaller, and then our boundaries are getting absorbed, right? So whenever you do the ping pong, it increases again, but then it decreases when it reaches the outer boundary. Now, this is the same video in which I hope that you can see the grid. I've overlaid the grid in here. Let's see, I cannot zoom in, unfortunately. Let's see if I do it like this. Maybe it's a little better for you to see, right? So here in this showcase, we have two levels of mesh refinement, just because I can, right? I just added a level of mesh refinement here in the center. And this is our Cartesian patch and our spherical patches joining together. Now here I have greatly increased or decreased the range of the plot, right? So like we are seeing we are able to see much smaller values. This is why our Gaussian pulse looks so big here in the beginning, this huge blob, right? This is, of course, to show you what happens when you go across the refinement levels and across the interpatch boundaries, right? You can see that because we have this sort of pillbox shaped grid, it becomes kind of like oblonged in one direction and so on and so forth, right? But the important thing is that now here you can see the back reflections more clearly, right? But the important thing is that if you let enough time pass, these things are going to be absorbed by our outer boundaries. So again, this is not very exciting because it's just a wave equation, but it still helps to show that things are working as they should. This is the same thing, but here we are doing a 1D slice, right? We can take a cut of the grid and we look at a side profile to see how the peaks of these waves propagate out. And I'm not just going to show you this once because I've talked enough about this, but you can see, that you get a little bit of back reflection, but then, things are just as they should. You absorb your pulses. Now, this is a showcase of how things work on a non-spherically symmetric Gaussian pulse. So here we are looking at a 3D plot, and I have these 3 slices, right? I have an X, Y, and Z slice of the grid, and I put them together like this. so that you can see this non-spherically symmetric Gaussian pulse evolving here. Right, and the same thing, you have your pulses evolving in your absorbing boundary conditions, right? And same thing, but now we have like a closer up of the grid. Again, I just added a level of mesh refinement just because I can, right? Just to showcase how these things propagate as they should out of the boundaries and how they get carried away and they eventually get absorbed. And of course, the holy grail of doing this, the applications that we're focusing on right now is binary black holes. Now that is still under work. What I'd like to show you is some preliminary waveform of a head-on collision that we ran, right? It's not perfect. There's a lot of kinks and lots of things that we have to figure out. This is a fairly coarse resolution run. So, lots of caveats here, right? But we are able to start, extracting some waveforms and getting some results with this. And I think things are going fairly well on that part. Finally, what I would like to show you in the final minutes of this talk is I would like to show you the code changes you would have to do in order to use this multi-patch system. And so for that, I'm going to pull up my code editor and I want to show you some code. So here, what we are looking at is the right-hand side of the wave equation evolution cactus grid function. And here is the CapyrX kernel that's going to compute that. Oh, and by the way, I didn't say this, but CapyrX is also GPU enabled. You can run this on the CPU and on the GPU. So what you're going to do here, basically, right, is what I am doing here is I'm trying to be clever and cute and doing some sort of optimization. So CapyrX gives us the point descriptor, which gives us a lot of information about the points that we're currently looping through, right? And I can tell if I am on a Cartesian patch or not, right? So what I'm saying here is that, okay, if I'm on a Cartesian patch, I just want to do regular finite difference derivatives. This is an x, a y, and a z derivative of the grid function of the scalar wave equation. And then I just combine them here as you would regularly. Now, if I'm not on a Cartesian patch, what I'm going to try to do, what I'm going to have to do is I'm going to have to do the Jacobian projections, right? Because I've mentioned that we are storing quantities with respect to a global Cartesian grid, so we have to do these coordinate projections. If you're familiar with Llama, you'd still do that with Llama. Llama tried to provide you some sort of way of doing that for you, but I don't think that's probably the right way to do. I think being more explicit in this case is better. So what CapyrX gives you is it gives you two data structure, which are called local first derivatives and local second derivatives. Now, these are very simple. They're just basically data bags. So you fill this struct with your local first derivatives. These are the derivatives you compute using your finite difference stencils, right? So the x, the y, and the z derivative. And you also fill another struct with your local second derivatives. The same thing. Then here you need your diagonal derivatives, but you also need your mixed derivatives, right? Here you have some handy functions to read the Jacobian grid functions that you're going to use for these projections, right? You need the Jacobians and the Jacobian derivatives of your coordinate transformations. Of course, you have to tell CapyrX that you're going to read these variables. CapyrX provides them for you, but you have to tell it you're going to read them. And then you have this handy function here, which is called project second. There's also project first. You project the first derivative or you project the second derivative. You pass your local derivatives and your Jacobians, and it gives you back a struct with the second derivatives. Right? So you pass the local second derivatives, and it gives you back the dx dx, dy dy, dz dz, and also the mixed derivatives of that. Right? So that's basically all of the code change that you have to do. So you go basically from this on a Cartesian system to something like this in a non-Cartesian system, right? So the steps are fairly simple. You compute your local derivatives, you read in your Jacobians, and you call project. And once you call project, this thing here contains all of your derivatives that you're going to need for your runs. Now, in the very, very last second of the talk, I would like to show you how this looks on an actual binary black hole evolution code, which is CanudaX. And you're going to see that the difference is not that big, So I'm going to navigate here to the CanudaX repository, CanudaX BSSN mall. And let's take a look at the BSSN right-hand side, which is a fairly complicated thing. Right? So Canuda defines these objects here, these functions, which are called compute first derivs. You pass in the point descriptor and the variables you want to compute the derivative of. Here, the difference, of course, is you're taking one or two extra arguments, either the Jacobians or the Jacobian derivatives. And if you inspect how these functions are implemented, right, you can just come here and you take a look at this. You're going to see that the algorithm for this is basically the same. So here's how you do it, right? So you compute your local derivatives using your finite difference stencils. You fill in these structs, you call the function, and you get the result. Right? It's pretty straightforward, and it should work easily for your code. And if your code, for instance, is like Canuda, in which your derivatives are computed like in a centralized fashion, it's really easy to adapt that. Now, I've been speaking for 40 minutes, so to finalize, to end things, I'd like to remind you that CanudaX is, I think, infrastructure-wise, is ready to be used. We're still trying to adapt it and make sure that everything works perfectly as it should on a binary black hole collision. And if you're interested and if you want to work with multiple coordinate patches and non-Cartesian systems, please take a look at CapyrX, consider contributing to it and adapting your science codes to it. There are 2 notebooks in the tutorial server that showcase how you can write parameter files for using CapyrX. It's just parameter files, so I'm not going to talk a lot about that. But you can see, you can just compare that basically parameter file-wise, the changes are very simple. So if you're interested and if you want to run these examples, especially the WaveToy Jupyter Notebook, I encourage you to run that. Through that, you should just run through it and it should just give you a nice waveform. There's also a very, very coarse binary black hole evolution in the tutorial server. Of course, you're not going to be able to do like a production run in a tutorial server, but it should give you an idea on how you set up a head-on collision parameter file using multiple coordinate patches and CanudaX. And I think that's it. If you have any questions and comments, I think that's the time to ask them. And otherwise, thank you for your attention.
Thank you very much, Lucas, for a very nice talk and tutorial.
I'm going to leave my references here just so you know, and that's it.
Yeah, thank you.